This is Group 12. Our topic is DJ, enabling high-density multi-tenancy for cloud gaming servers with dynamic cost-benefit GPU loading balancing. The authors of this paper are Sergio, David, Alec, and Roger, and the presenters today are Chiyu-Lin, Kasima Bulan, and Jayashi Pridivi. This is Chiyu-Lin. We can start now. Before talking about our topic, let's have a short look for some keywords that we will mention in this paper. The first one is frame rate, the frequency at which consecutive images called frames appear on the display, which is also known as frames per second. That's a moving scene we saw in our normal life. It usually applies to film and video cameras, computer graphics. And the second one is rendering. Rendering is a process of generating an image from a model by means of a software program. It is also used to describe the process of calculating effects in a video editing file to produce final video output. A rendered image can be understood in terms of a number of visible features. For instance, shading is how the color and brightness of a surface varies with lighting. There are a lot like reflection, transparency, so on and so forth. Motivation. According to the paper, the authors mentioned there are some major problems within cloud gaming, which are latency, bandwidth, and multi-tenancy. Latency and bandwidth have been talked in other resources. It's here. So the main problem the authors want to solve is multi-tenancy. Talking about multi-tenancy, the SAM isolation and virtualization support that has served traditional host service well would surface for multi-tenant gaming also. However, cloud gaming multi-tenancy is challenging and distinct from traditional data center multi-tenancy. The reason is that games exhibit three unique properties, which are GPU-centric workload, continuous deadlines, adjustable visual quality. But what caused multi-tenancy being a problem of cloud gaming? It's GPU processing. For gaming, GPU processing is a bottleneck resource. One avenue to multi-tenancy is to create a static partitions of the GPU for each application instance. Because we have to manipulate multi-tenancies who want what they are going to experience always has the highest quality. It means we should take care of their satisfactory of the gaming experience and also the availability. Commercial GPU visualization solutions from Citrix and VMware already provide this capability. However, this leads to very poor server density for two reasons. First, users come and go, making static partitions unaccommodating. Second, a game scene complexity and corresponding GPU load can change dramatically over time. For example, a user in a virtual environment may view a simple room at one moment, and then navigate to view a complex garden environment in the next moment. Unfortunately, a static partition must allocate conservatively for peak load, since poor frame rate during some scenes is unsatisfactory. This means during any non-peak load, which occur frequently, GPU cores sit idle. This waste leads to inefficient operations on the part of the service providers. So the mission to the topic is to find a balance between availability and resource wasting. Then, how to deal with presenting these two kinds of scenes. These two scenes are just like what we mentioned in the last slide. A simple scene and a complex scene. If a server chooses to statically provision for the worst case of all players visiting complex scenes all the time, which means allocating for peak load, wasted resources and over-provisioning will be significant. Naively, running multiple tenants concurrently on the server can pose grave shortcomings. A load generated by one instance can squeeze out another instance, resulting in missed deadlines, low or erratic frame rates, and an unplayable experience. Even the load generated by a single instance exhibits significant temporal variability due to scene complexity. Simple scenes with a few basic objects and no effects, such as figure A, render much faster than complex scenes such as figure B. Players can encounter both simple and complex scenes within a brief window of a single session. These are why the authors built DJ to address these shortcomings. They care about 2 points, which are cost in terms of GPU time and benefit in terms of visual quality. Utility is the basis for DJ's 3 main functions which enable it to maximize aggregate visual quality, and we will talk about it later. Now, let's see if this is an important problem. Of course, yes. How to provide client satisfaction in visual quality, being stable and available all the time. Obviously, every player wants to play a game smoothly. Due to different objects leading different using in GPU level, we would fail by allocating fixed resources to all things, so we must give in the most resource of GPU to our client, but it causes GPU idle. If the GPU is scalable, then it would not be a big problem. However, the problem is how fast we are able to adjust the amount of GPU that we are going to allocate to our client. I'm going to extend the previous slide by adding this additional question. Is there any other issues? Yes. We talked about the problem of scaling is how fast we are able to adjust the amount of GPU that we are going to allocate to our client. In briefly, the main thing this paper has done is to estimate the utility. We now know how much resource we are going to allocate, right? But the problem of how fast we can give wasn't mentioned. If the speed of scaling isn't that fast, a potential problem would be delay, and delay causes bad user experiences. Moreover, it's about money. If I have a gaming server, I should know how much resources are going to be scaled could lead to the minimum cost. And I want to make sure the cost is always the lowest it is supposed to be. Also, it should satisfy all my customers and be stable. That's why I think there are some issues not being included in this paper. We need to think about the whole process to deal with the problem. Did the authors motivate convincingly this problem? This is relevant to the previous slide I added. They do care about the cost of GPU time and how to estimate the distribution of GPU resources to clients. They want to find a solution to address the shortcomings of creating static partitions of the GPU for each application instance. But there are more problems related to this issue, just like I said in the previous slide. Is the importance theoretical, practical, or both? It's both. In theoretical, it is important. If the amount of users increased, we can calculate how much loss the server would encounter. In practical, the authors have applied DJ on real productions, and we know it does help. Are there any solutions out there for this problem? There is a solution from NVIDIA in 2018. If there is an advanced GPU virtualization, it would be a solution to dynamically scaling. According to developer.nvidia, Kubernetes on NVIDIA GPUs enables enterprises to scale up training and inference deployment to multi-cloud GPU clusters seamlessly. It lets you automate the deployment, maintenance, scheduling, and operation of multiple GPU-accelerated application containers across clusters of nodes. In short, we can dynamically scale GPU to nodes very fast by buying GPU clusters. We know that GPU was not able to be split without GPU virtualization in the past. In order to improve the performance, we can only add one GPU at one time, but we still don't know how much GPU we should provide to our services, and the speed to respond to demand is slow. Kubernetes on NVIDIA GPU actively monitors our operation and allocates resources we need. Due to the availability of GPU virtualization, allocation of GPU resources are accelerated. The utility of GPU clusters are optimized by monitoring the operation. You can learn more in the video of 2018 Kubernetes, a keynote at the GPU Technology Conference. And this part starts at 1 hour 11 minutes and 13 seconds. What are the similarities and differences between this work and existing solutions? The similarities is to solve the using of GPU resources in the cloud. The differences are, first, DJ uses pre-calculation. They estimate their utility, and NVIDIA uses scaling. Second, the difficulty of parallelization in gaming and machine learning are different. In machine learning, they just added trend model copy into computation cluster. And DJ is stateful. Then NVIDIA is stateless. We should pass the current situation to it when we add new resources to make sure the continuous of our game. These two solutions do help when we are talking about the problem of lacking GPU resources. Only when we are in the implementation, there are something inside and outside the structure should be adjusted due to issues of network or others.